Welcome back to my channel, Knowledge Spread by Sir Boots. This time we are going to deal with probability distribution of the discrete random variable. But let me first greet my students from AIM A, B, C, as well as from tourism and sports and arts and design and dress making. So let's proceed. Okay, our objective in this video is to present the probability distribution through table, mass function, and through graph. So let us remember, in tossing a coin twice, the possible outcomes are S equals HH, TH, HT, and TT. It means head, tail, tail, and tail, tail. If we account the number of heads, there are 2 heads for HH outcome. 1 for TH and HT outcomes, and 0 head for TT outcomes. Since there are 4 possible outcomes, the possibility of having an outcome of 2 heads is 1 out of 4 or 1/4. And the probability of having an outcome with 1 head is that is TH and HT is 2 out of 4, so 2/4. And the probability of having 0 head in the outcome is, that is TT is 1 out of 4. So that is 1/4. Then the random variable x equals 0, 1, 2, and its corresponding probability is presented in the table below. So for the random variable x, that is 0, 1, 2, and the probability that 0 head comes out in the outcome is 1/4, and the probability that 1 head comes out in the outcome is 2/4, and the probability that 2 heads comes out in the outcome is 1/4. So this table, which is shown, is the table called the table of discrete probability distribution from this experiment of tossing a coin 2 times. So from the given example, we can see that the values of the probability f of x ranges from 0 through 1. That is, in notation, we have p of x is greater or equal to 0, and p of x is less than or equal to 1, where p of x is the probability. Also, if we add the probabilities, the sum is 1. So these are the properties of the discrete probability distribution. If x is a random variable with n elements, then each of the probabilities p of x or p of x uppercase x equals lowercase x. This is just the same as p of x, because other books write p of x as p of uppercase x equals lowercase x, has value which ranges from 0 through 1. And number 2, the sum of the probabilities that is P of x sub 1 plus P of x sub 2 plus P of x sub n equals summation of P of x that is equal to 1. Which means if you add the probabilities 1/4, this is the probability, remember? And this is the random variable. So if we add the probability, this one, probabilities 1/4 plus 2/4 plus 1/4, that is 4/4, and that is equal to 1. That is explicitly stated in the property of the discrete probability distribution, that the sum of all probabilities in the discrete probability distribution is equal to 1. Now let's apply that probability. Tell if each of the table below defines a discrete probability distribution. The random variable are x, 1, 2, and 3. And the probability f of x equals 1/5, 2/5 equals 2/5. How to detect that it is a table of discrete probability distribution? You go to the probability, whether it is between 0 through 1. Okay, so it is 1/5, so less than 1 but greater than 0. 2/5 is less than 1 but greater than 0. And 2/5 is greater than 0 but less than 1. And if you add 1/5 plus 2/5 equals 3/5 plus 2/5 equals 5/5. 5 divided by 5 equals 1. So this table number 1 is a table of a discrete probability distribution. For number 2, we have the random variable 0, 1, 2, 3, and the probability of x equals 1, 8, 2, 8, 3, 8, and 2, 8. So the probabilities are greater than 0 but less than 1, and the sum of the probabilities are 1, 8 plus 2, 8 equals 3, 8, and 3, 8 plus 3, 8 equals 6, 8, plus 2, 8 equals 8/8, and that is equal to 1. And therefore, this number 2 table is a table of the discrete probability distribution. Okay. So, the table of the random variable and its corresponding probability is one way of presenting probability distribution. But there are still other ways, no? That is through probability mass function. That is another way of presenting probability distribution, probability mass function. Let us recall that the corresponding probability of random variable x is p of x, and we can express it as an ordered pair. That is x, p of x. So the domain is x and p of x is the range. So in this case, the discrete probability distribution becomes probability mass function. Now, if we account the number of heads that come out in tossing a coin 3 times, the sample space would be, to get the sample space or the possible outcomes, in a coin there are 2 faces, and we make that as the base, and the number of tossing a coin is the exponent. So if we toss a coin twice, the base is 2, and the exponent, if we toss a coin twice, the base is 2 and the exponent is 2, that is 4. But if we toss a coin thrice, then the base is 2 and the exponent is 3. 2 raised to 3 is 8. That's why in the sample space, S is equals to H T THH, HTT, TTH, HTH, THT, and TTT. And so, there are outcomes that where there is no head, and that is TT, T. No? And there is also an outcome where there is only one head in the outcome. That is HTT, THH, TTH, and THT. And there is also outcome where two heads comes out, no? Like HHT, THH, and HTH. Okay. And there is only an outcome where three heads are there, like HHH. Thus, P of 0, now P of 0 is equals to 1/8. And P of 1 is 3/8. And P of 2 equals 3/8 also. And P of 3 equals 1/8. So this P of 0, meaning there is 0 head that come out, and that is T. So only 1/8. And P of 1, meaning there is one head in the outcome only. So how many are there? So this one, it's TTH and THT. So 3 out of 8, so 3/8. And also for two heads, there are 3/8 outcomes, and for three heads, there is 1 out of 8 outcome. So this is already the probability mass function. So the discrete probability distribution is now presented through mass function. Okay. So the third one is the importance. I would like to express the importance of writing discrete probability distribution as a probability mass function. Why should we also know how to write the discrete probability distribution as probability mass function? Is when the values of random variable is too many, and that is when the listing is practically impossible. Like in tossing a coin thrice, like we had in our above study, no, the total possible outcome can be written through formula. These two are the faces of a coin, and 3 is the number of times the coin is tossed. And the result is 2 raised to 3 is 8. And this becomes the denominator of our function. So it can be written as f of x equals 3c sub x over 8. This 3 represents the number of times the coin is tossed. This c is the coin, and x is the number of heads that comes out. No? If the head is accounted in the experiment. So that becomes our value of x, which is for x equals 0, 1, 2, 3. Which means that for 3c sub 0, that means 3 tossing of coins, but 0 heads come out. That is equal to 1. And also, the second is 3c1. You toss a coin thrice, but only one head comes out, so that is 3 outcomes. Also, this one, 3 coins, 3 tossing of coins, and there are 2 heads that comes out. There are 3 outcomes also. And 3 tosses of coin and 3 heads come out, there is only one outcome. So that is it, no? So, and repeat, the probability mass function can also be written in tabular form, the same result, no, as we are going to present it is in the table. Now, the other one is to present this as a histogram. Oh my God, the vertical line I draw is not perpendicular, but you just assume that this is perpendicular. As well as this line, it seems that it is inclining down, but that is really a horizontal line. You just imagine that this is a horizontal line. So the random variable is in the horizontal line. Do not place 0 here. It should be here, no? A little bit farther from this corner. 0, 1, 2, 3, and the probability is here. Starts from 1, 8, 2, 8, and 3, 8. So in drawing a histogram, you write a line, you draw a line between 0 and 1, and going to 1/8 because there is a 1/8 probability for 0 heads to come out in the outcome, so it is 1/8. So you draw a line until 8, no, you connect and shade, and from that line you between 1 and 2 you write also a line, and since 1 is since 1 head comes out in the outcome, there are the probability is 3/8, so you draw a line going to 3/8, connect, no, here also extend to 3/8, connect and shade. The same way here, so 2 from 2 to 3 you write a line in between, and since 2 heads comes out in the outcome of 3 outcomes, so 3 outcomes, so go to 3/8 as probability, so you just shade. And for 3 there is only 1 outcome, so 1 out of 8, so 1/8. So draw a line here, calculate that it's the same width as the other 3, and connect to and draw a line towards 1/8 and connect here and shade. So after that, we have already drawn the histogram, and we had presented the discrete probability distribution also through histogram. So we have presented already the discrete probability distribution from the experiment tossing a coin thrice, accounting the number of heads in the outcome, in 3 ways, that is through table and through this probability mass function, and also through histogram. Next, we will apply, no? We will tell whether or not each of the item described below is a discrete probability distribution, or tell whether or not each of the item below describes describes a discrete probability distribution. So in knowing that, we have to remember the properties of the discrete probability distribution, where the range of the probability is greater or less than 0, or equal to 0, greater or equal to 0, but less than or equal to 1. So this qualifies that first property, and this one. So And also, we have to find the sum if it is 1. So, 2.2 plus 0.1 is 0.3. 0.3 plus 0.6 is 0.9. 0.9 plus 0.05 is 0.95. And 0.95 plus 0.05 is 1. Therefore, this first table is a table of discrete probability distribution. The second one, now A is a random variable 1, 3, 5, 7, and its corresponding probability P of A is 0.2, 0.1, 0.6, and 0.05. This probability qualifies the property number 1, which is ranging from 0 or equal to ranging from greater than or equal to 0 and less than or equal to 1. But for the second property, let us find out 0.2 plus 0.1 equals 0.3, 0.3 plus 0.6 equals 0.9, plus 0.05 equals 0.95. It has not reached 1, and therefore, this is not a table of the discrete probability distribution. Number 3. P of X, it is P of X equals X over 3. For X equals 0, 1, and 2. So, we substitute these values of X and add them if it reaches 1 or it's, we will find out if this is 4. It describes discrete probability distribution. So, 0 over 3 equals 0. 1 over 3 is 1/3. And if X is 2, 2 over 3 is 2/3. So, 1/3 plus 2/3 equals 1. So, this is also a discrete probability distribution. Okay. Now, for evaluation, write the probability distribution of the random variable R, representing the number of red balls when 3 balls are drawn in succession without replacement from a jar containing red balls and 4 red balls and 5 blue balls. Okay. So, again, there are 2 kinds of balls, red ball and blue balls. So, that is our base 2. And we're going to draw 3 balls in succession. So, that is our exponent. 2 to the third power equals 8. So, that is the formula. So, we get the number of possible outcomes as 8. Okay. So, there are 2 kinds of balls. And 3 balls are drawn in succession without replacement. Therefore, to know the number of possible outcomes, we use the formula 2 raised to 3 equals 8. And the sample space are BBB, BBR, RBB, RRB, BRR, BRB, RBR, RRR. B stands for blue balls and R stands for red balls. Then the probability mass function would be listed below. Okay. This is the table for that discrete probability distribution 0, 1, 2, 3 because there is an outcome where 1 red ball only comes out and 0 red ball also comes out. That is 1/8 and 1 red ball comes out, that is the probability is 3 over 8. Also 2 red balls comes out, that is 3 over 8, and for 3 red ball only 1 over 8 in the possible outcome. So this is the table, no? So here it is already presenting the experiment as a discrete probability distribution through mass function. So in this case, P sub O equals 1 over 8, P sub 1 equals 3 over 8, P sub 2 equals 3 over 8, and P of 0 equals 1 over 8, P of 1 equals 3 over 8, P of 2 equals 3 over 8, and P of 3 equals 1 over 8. So again, that is presenting the discrete probability distribution through mass function. And for the histogram, so this is the histogram. That is the same as we are tossing a coin, because in tossing a coin thrice we have also 8 outcomes. So that's the same histogram can be presented here. Okay, so let's go to testing ourselves. Now we test ourselves. Let's make it clearer. It's quite unclear here. Let's try to make it clear. No, it's random variable table. Okay. Testing yourself. No, test yourself. You comment down your answer in the comment section if you wish to. A coin is tossed 4 times and provide the following. Letter A, sample space. Random variable, accounting the heads of all possible outcomes. Then present it in the table. Then present also as a probability mass function and also histogram. That is test 1, no? Test yourself 1. Then we have test yourself 2. Identify whether or not each of the item below describes a discrete probability distribution. So we have this table, P of X. I hope that you can read. And this is in number 2. It's quite unclear. I hope that you can read it. Okay, and this one, I hope that you can read also. P of R. So these are the questions. Also here, number 3, I will make it clearer. Okay, and this one, I hope this will be made clear. And also this one, no? And this one. So you just comment down your answer if you wish to in the comment section below. Thank you very much.